Hello again. There's a strong possibility that you're coming from just watching the numeric basis video, but if not, or either way, welcome. This video is going to talk about numeric representations in C, both the way they are represented insofar as the way you type them in your program, and also the way they're represented as far as how they're stored in bits on the disk or in memory. So that's what today's going to be about. Today, this lecture, this content, whatever. So we've already seen some examples of numeric literals or numeric constants in C. So there were a lot of examples in the printf, scanf lectures. And in many cases, they work exactly how you would expect. You save a number, 42, into a variable, and it saves the binary representation of the decimal value 42 into computer memory. But for other kinds of literals, including cars, floating point numbers, and octal hexadecimal literals, there are some subtleties. So first, for integer literals, if you want to create a literal integer, just type the decimal representation of that number. With one exception, one important exception, the value cannot have a leading zero or zeros. That is, if you want to store the value 17 in a variable named score, you would use int score equals 17 semicolon, not int score equals 017. This will not do what you expect, and we'll talk about why in a minute. I don't think many of you would have been doing this anyway, but just so you're aware, when you're putting in a float, when you're putting in an int, don't put a zero at the beginning, just write the number. And generally, an integer constant will be stored internally with type int. If by chance it is too large to fit in an int, that is, it is bigger in magnitude than 2 to the 32 on most computers, it will be stored with type long int. To create an octal literal in C, just type its value in octal with a leading zero, and the leading zero here is mandatory. That's why you couldn't type an integer with a leading zero, a decimal integer with a leading zero, because C would try to treat it as an octal value. So int score equals 17 saves the decimal value 17 into the value named score, while int score equals 017 saves the octal value 17, which is the decimal value 15, into the variable named score. If you want to create a hexadecimal literal, just type its value in hexadecimal preceded by either 0 lowercase x or 0 capital X. So 0x, your number, is how you type in a hexadecimal literal. So int score, once again, equals 17, saves the decimal value 17 into the variable named score, while int score equals 0x17 saves the hexadecimal value 17, which is equivalent to the decimal value 23 into the variable named score. And one more thing, for the letters in a hexadecimal constant, case doesn't matter. So A, B, C, D, E, F, and X can all be either lowercase or uppercase. You can mix them in any order you want. It doesn't matter. 0x, A, B, C, D, capital X, A, B, C, D, lowercase x, capital A, B, C, D, capitals, all caps, A, B, C, D. They're all the same. They all represent A, B, C, D, which is decimal value 43981. So this is going to come in handy. We mentioned during the bitwise operators discussion that if you wanted to set multiple bits of a value to 1, you would OR it with an octal or a decimal value with the appropriate bits set to 1. Now you know everything you need to know. You can figure out which bits are set from the discussion in the numeric basis lecture, and then you can set them by creating the appropriate octal or hexadecimal value and then just typing it in as either 0, your number, for an octal number, or 0x, your number, for a hexadecimal number. A quick digression that isn't really going to come up in this subject, but it actually did come up a little bit today in lecture. So if you were in the lecture hall for lecture 6 on Thursday, March 21st, there was some discussion of why we were using unsigned cars instead of just cars. And that's because negative numbers behave weirdly when you look at their bits. So in the numeric bases video, we talked about how to convert binary numbers to their decimal equivalents. But notice that the formula we used could only result in positive numbers. So we did the summation from I equals 0 to k of symbol I times n to the I, where symbol is always, by definition, greater than or equal to 0. So for this, any number in a base you can represent as long as it's positive. But integer values can be positive and negative. So how do you represent a negative number in binary? And it turns out that there are several ways to do it, and C does not specify which one a computer uses. So negative numbers and bit patterns don't mix well together because it's undefined behavior. C doesn't know how the computer actually stores the negative number on disk, which is a problem. So the most obvious way is just to add an extra bit that represents the sign. This is called sign and magnitude form. So to hold a number between negative 2 to the n minus 1 and positive 2 to the n minus 1, you would need n plus 1 bits. N bits to hold the magnitude of the number, and one more bit to hold the sign. So to write 5 in binary, you would write it as 0101 if it were positive, and 1101 if it were negative. So the first bit of a number determines whether it's positive or negative. So a couple of observations about this. One is that you only get 2 to the n minus 1 possible values out of n plus 1 bits, not 2 to the n as you would expect. And why? So you have to think about how 0 gets represented. In sign and magnitude form, you can have positive 0 and negative 0, which is weird, right? And it also creates some weirdness when doing math. So for that reason and some others beyond the scope of this subject, it's really hard comparatively for the computer to do maths on values that are in sign and magnitude form. So because of that, even though it's conceptually simple, it's rarely used in actual computers. Most computers don't use sign and magnitude form. Most computers use what is called 2's complement form. So the actual details are far beyond the scope of this subject. I'm not going to talk to you about how 2's complement works, but approximately 2's complement starts every value at negative 2 to the n and then adds to that. So every number starts at negative 2 to the n, and then you add whatever number is in the actual bit pattern. That hides some subtleties. It's not exactly right, but it's pretty close. So the minimum value that you can represent with n bits is negative 2 to the n, and the maximum value that you can represent with n bits is 2 to the n minus 1. So that gets us our full range of 2 to the n possible values, 2 to the n plus 2 to the n minus 1 plus 1 for 0. And it eliminates the potential of positive and negative zeros, and it also enables efficient arithmetic on the hardware. So this is what most computers in the real world actually use, 2's complement form. You can look it up if you're curious about it. There's a good Wikipedia page, but it's more complicated than you need to know for the purposes of our subject. So signed and unsigned integer representation. So despite the fact that 2's complement is good in a lot of ways, the C specification does not define what representation is used internally for signed integers or signed cars. This is so-called implementation-specific behavior, and it varies depending on the specific computer your program will be running on. So let's assume you try to put the value ABCD in hexadecimal into a signed int. The binary representation of that, which you could compute if you wanted to from the numeric bases lecture, is 1010111111001101. Note that the first bit of this is 1, which means that it represents a negative integer in either sign and magnitude form or 2's complement form. And what negative integer is it? Who knows? C doesn't know. It depends on which computer you're running it on. So doing anything with this value will result in undefined behavior, which is bad. We don't want undefined behavior. We want defined behavior. So if you care about the bit pattern of a number, if you want to put an octal or a hexadecimal value into a variable, always use unsigned ints or unsigned chars. So the example from a few slides ago should really not have been int score equals 0x17. It should really be unsigned int 0x17 or unsigned int 017. You should always use unsigned integer or char representations when you're using hexadecimal or octal values in them. A related issue to that, somewhat related to the sign and magnitude 2's complement discussion, is arithmetic overflow. And that's what occurs when the result of a mathematical operation is a number that is too big to hold in the variable. So for example, on most computers, a signed int is stored in memory as 4 8-bit bytes, so 32 bits total. So on most of those computers, the maximum value that can be stored in a signed int is 2 to the 32 minus 1, which is 2,147,483,647. What happens, do you think, if the result of a mathematical expression is, let's say, 2,147,483,648? Let's find out. So I wrote a little program called overflow.c, and I defined an integer variable called almost, which is 2,147,483,647, and an integer called too much, which I've initialized to be 0. And then I print out the value of almost, and then too much is equal to almost plus 1. And then I print out the value of too much. So almost is the maximum value that can be stored on most computers in an signed int. If I add 1 to it, it's too much. So if we look at the output, the first number works just fine. We print out almost, we see the number almost. It's 2,147,483,647. If we add 1 to it, we should get 2,147,483,648. But instead, we get negative 2,147,483,648. We are wrong by literally the maximum amount possible because of arithmetic overflow. The sign bit has been flipped when it shouldn't have been. Good thing this code wasn't controlling a rocket or something, because we're wrong by a lot. Unfortunately, at least in C, there's nothing you can really do about arithmetic overflow. Sometimes you're going to do math with big numbers, and they might overflow. But it's just something you should be aware of as at least a possibility. So if you're doing some maths and you get a result that is much smaller, much more negative than it seems like it should be, or has entirely the wrong sign, you may be seeing the symptoms of overflow. So maybe you should consider using long ints, or long floats, or long doubles as appropriate. I guess long floats aren't a thing. That's just a double. My apologies. Other types of literals. We have char literals. To have a literal character, you may have seen this in the last lab. You do that by putting a single character within a set of apostrophes or single quotes. So for a character that is on the keyboard, just put that character in single quotes, like A in single quotes, or capital A in single quotes, or 1 in single quotes, or the ampersand in single quotes. For a character that has to be represented by an escape sequence, see the printf lecture for more on that, put the whole escape sequence between single quotes. So single quote \n single quote still represents a single character. Even though it's 2 characters typed out, The escape sequence represents a single character. It represents the new line character, or the tab character, or the backslash character. And just so you're aware, a car literal is actually stored as a type int. So that's why in the lecture this morning, I had to cast the result of a not to unsigned car, right? Because it's stored as an int. The result is an integer. I had to cast it to an unsigned car. But cars are just small ints, so it's okay to do that. For floating point literals, the literal must contain either a decimal point or an exponent. So you can represent 42 in a lot of ways as a floating point number. You can say 42 dot, you can say 42.0, you can say 4.2 E1, which is 4.2 times 10 to the first. You can say 420 E minus 1, so 420 times 10 to the minus 1. Those are all floating point values. If you just type 42, if you type the numerals 42, that's an integer. That's not a floating point value. And generally, a floating point constant will be stored internally with type double. So if you really want it to be single precision, if you really want a float, you append the literal with F or capital F. So 3.14159F gives you a floating point number, a float, not a double. If you really need, you probably don't, but if you need extended precision, if you need it as a long double, append the literal with L, either a lowercase or a capital L. So 3.1415926535897932385L will give you the representation of pi as a long double. Unlike the signed integers, C does specify how floating point numbers are stored in memory. They must adhere to IEEE standard 754, which we talked about briefly back in lecture 3. But to you, it doesn't really matter, because as a programmer, you should never, ever, ever try to manually manipulate the bit patterns of floating point numbers. You should always be using unsigned ints, unsigned shorts, unsigned cars, unsigned long if you really need a lot of digits, but you should be using unsigned integer representations if you care about their bit pattern. So to recap, we just talked about how to write literals. Integers go as expected. To write an octal value, you put a 0 before the value in octal. For hexadecimal values, you put 0x before the value in octal. For a car, you put the car you want in between apostrophes or single quotes, and it gets stored internally as an int, so be careful with that. Cast it to a car if you need to be sure. And for floating point values, they must contain a decimal point and or an exponent. Always put your octal or hex values in unsigned ints, and be aware, at least, of the possibility of arithmetic overflow when working with very large numbers. That's it for this discussion. Thank you very much. Be well. See you next time.